Welcome back. For the last few lectures, I kept dropping little asides about how there are problems with null hypothesis significance testing, and that there are alternatives that can sometimes be more valuable. In this lecture, we'll cover a few of those alternatives and why they might be useful. But notice before we go on, I didn't dismiss significance tests, even in their strictest form of hard cutoffs. NHST remains both common and useful, as well as providing a shared language to help scientists in many disciplines understand each other's results. The major problem with NHST is revealed in the old proverb: when all you have is a hammer, every problem looks like a nail. For too long, NHST has been that hammer, and unfortunately for star enthusiasts, not every sociological problem is a nail that can be hammered with just a significance test. One of the most important limitations of significance tests is that they don't tell us anything about whether an effect is meaningful, only whether it's likely to be an artifact of sampling. The better your sampling, and the larger your sample, the more likely you are to find a significant effect, despite the fact that the effect is the same in both circumstances. With large enough samples, even a minuscule difference can be highly significant, because the test will have sufficient power to distinguish statistics that are practically identical, but significantly different. The approaches I'll talk about today all attempt to get at the substantive importance of an effect, that is, a relationship, rather than providing direct tests of the probability that it's due to sampling variability. Even so, each of these can be combined with a modified NHST framework in some way to provide tests of both. They're all measures of what's called effect size, that is, the strength of a relationship. So, one common effect size measure is Cohen's d. It's written up here. You see it written as a lowercase d, and it compares the value of a statistic between two categories or groups. When the categories have the same standard deviation, which is rare but sometimes approximately true, or when one category can be considered a control group, like in an experiment, and provide a baseline, d is simply the difference between the means. Notice they're sample means, so they're x bar instead of mu, divided by the standard deviation. It's essentially a group level version of comparing two standardized z-scores. When standardized deviations differ, calculations can become more complicated and require an average standard deviation. Because larger samples provide more stable estimates of standard deviation, d is weighted by the size of each sample. So the smaller category is less influential in calculating the standard deviations, but has the same weight in calculating the mean difference. Now, unlike statistical significance, however, only the relative size of groups matters for Cohen's d. All else being constant, a larger sample will produce the same estimate as a small sample, as long as the groups are the same size or the same ratio. This prevents the problem of finding significant but meaningless effects, but it is prone to error in small samples when the standard deviation happens to be low in the sample, causing type 1 error, or too high, causing type 2 error. Now, one of the effect size measures you're most likely to see is Pearson's correlation coefficient, or R. Correlation can be used with one continuous and one binary variable, just like d, but it can also be used and is even more useful for two interval or interval-like variables. And unlike Cohen's d, it's not scaled in terms of standard error. Instead, it has a range that goes from -1 to +1. A correlation of 1, seen up here, is perfect positive correlation. That indicates that two variables can predict each other perfectly. You only need to know one to know the other. So if one goes up by a certain value, the other goes up by a proportional value. It may not be the same value, they may not each go up 1, but they always go up in lockstep. A trivial example is the correlation of today's date and tomorrow's date. For every today, tomorrow will be exactly 1 day later. The difference doesn't have to be 1. You could just as easily have said the correlation of today and the day after tomorrow, or today and 27 days from now. Perfect negative correlation, seen in the bottom right here, is the exact opposite. Two variables move in perfect tandem but in opposite directions. A trivial example of this is the proportion of people who agree with a statement and the proportion who disagree, assuming there are only two answers they can give. As one goes up, the other inevitably goes down by the same amount. A zero correlation means the variables are unrelated. Higher values of one, the x variable, don't predict higher or lower values of the other. Uncorrelated variables are also sometimes called orthogonal. Now in practice, it would be very unlikely for any meaningful social variables to have perfect or zero correlations, either in the population or in a sample. But the value of r tells us the effect size and the direction of the relationship. So you see an r of 0.5, it's about a quarter as strong, because we'll talk about why it's a quarter instead of a half, as an r of 1. But we can compare these regardless of the sample size, regardless of the standard deviation, regardless of the type of variables. Now, it's worth noting that r is also tied up with variance in the sum of squares. Often, models will be reported with an r squared statistic in the papers. R squared can be understood in two ways. First, it's the square of r, Pearson's correlation coefficient, between two variables. But it's also equal to the proportion of variance in one variable that can be explained or predicted by another variable or model. So if you look at the bottom left here, recall that the variance of one variable is the average of the squared errors using only this mean, this y bar, to predict. So the errors would be the distances between each of these and the line. The sum of squared errors would be the sum of squares of all those differences. If we have a variable predicting it, and we have, say, this line here, the difference, the improvement or the decrease in the sum of squares between this mean and this is the r square. Now, for two binary variables, odds ratios provide a third measure and an intuitive measure of the relationship strength that, as a bonus, is simpler to calculate than correlation. Once you get past one hurdle, you must remember that odds are not the same as probability. It's hard because in everyday speech we often use odds and probability interchangeably, but in statistics they're only related. Recall, the empirical probability of an event is the number of times it happens out of the total number of times it could have happened. That is, successes divided by trials, or occurrences divided by trials. The empirical odds of that event have the same numerator, the successes, but the denominator is the number of times it didn't happen instead of the total. So we would say successes divided by failures, or yes divided by no. So odds are a ratio of yes to no, or 1 to 0, while probability are a ratio of yes to yes plus no. For an example, our class meets 4 times a week, one of which is a lab session. If you randomly missed one class session in a week, the probability that it's a lecture is 3 in 4, or 0.75. But you could also say you're 3 times as likely to miss a lecture as a lab. That 3 and 3 times as likely is the odds of class being a lecture. By converse, you could also say you're 1/3 as likely to miss lab as lecture, so the odds of that class being a lab would be 1/3 instead of 1/4, which would be the probability. Odds equal to 1 mean an equal chance of yes or no. The top and the bottom are the same. Note the difference from correlation, which is centered at 0. Values range between 0 and 1 when the probability of no is higher than yes, and values are greater than 1 when the probability of yes is higher than no. So that gets us as far as one variable. Odds ratios go a step further by combining two variables in an odds of odds. Imagine you could choose instead to take the same class in the summer, but it would have 3 lectures and 3 labs weekly, an odds of 1. In everyday speech, you'd say labs make up 3 times as much of the summer class as they do of the regular one. Statistically, that's calculated by dividing the odds of labor in the summer, the odds of S given x equals 1, by the odds of lecture, in summer, by the odds of lecture in spring, the odds of S given x equals 0. It is a ratio of odds to odds. Now, an odds ratio is just that, the ratio of two odds values, the odds in two different categories of the same variable, to each other. It might be useful not only for choosing classes, but for example, for deciding what game to play in a casino for the best odds of winning something, and for many other things. Now, all three of these effect size measures, Cohen's d, Pearson's r, and odds ratios, are particularly useful in comparing results from different sizes of samples, because they're not inherently biased towards stronger findings just because you have a larger sample. But a caution: if either or both categories are very small, estimates can be unstable in any of these, regardless of the size of the overall sample. In practice, effect sizes of some sort and null hypothesis significance tests are most often reported together, frequently as a numerical coefficient, or correlation, or ratio, with a marker, like an asterisk, to show numbers with an estimated alpha of less than 0.05 or 0.01, for example. The researcher must use the sample size and variances to decide which to emphasize in their reporting. For extremely large or very small samples, effect sizes are often more meaningful than significance tests because they don't depend on sample size as much. For medium-sized samples, both can tell us important but different information about relationships. So hopefully that helps clear up why, when, and how you might use some alternatives or complements to NHST, as well as how they relate to other things we've seen. Other alternatives, such as meta-analysis and Bayesian statistics, are gaining acceptance in the scientific community, and I encourage you to learn a little about them if you have a chance, but this will at least get your feet wet and help you understand some things you're likely to see. So thanks for watching. See you again soon.